distance time graphs. So we've already looked at average speed, and we know that to calculate average speed, we need to know the distance traveled and the time that it took for us to travel that actual distance. So, in terms of graphs, graphs are used to communicate quantitative information visually. Great way to be able to compare, I guess, the average speed between two objects is by graphing both of them on the same graph. And by looking at the way the graph is shaped, that can pretty much help you identify which of the objects traveled faster. For your balloon car, in your booklet, you will be expected to have graphs because you are expected a minimum of 10 successful trial runs for your booklet. So remember, bless you. So remember that you are also going to include that in your booklet, which is due April 3rd. So on a graph, we can see whether the dependent variable increases or decreases with the independent variable. So we're going to look at which is the independent and dependent variable. On a distance time graph, time is usually the independent variable. We plot it along the x-axis. Whenever we graph, we will be graphing with time being on the x-axis. So it's the independent. So let's look at our x-axis here. So we have time, which is the independent variable. Distance is the dependent variable, and we plot that on the y-axis. Please note, whenever you are graphing, you always want to title your x and y axes. And we no longer call them x and y once we graph them. In terms of math, we label them as x and y. But in terms of, if we're plotting distance versus time, x is going to be the t. This y is now going to be designated as d. And please note as well, the title with specific units. Don't write the word units. You write the actual units that you're using. Are you using seconds? Are you using minutes? Are you using hours? For distance, same thing. Make sure you list your units. You do not need to graph it and write down this is the dependent variable. You're just supposed to know it. Same thing with here. Once we have, let's say, our points that we plot, we draw what we call a line of best fit between the actual points. And make sure you try to include as many points as possible to fit relatively close enough to that line of best fit. A running white-tailed deer. So here we have the following points. So we have our points that we're going to plot on our table. We have distance, we have time. Note the number of significant digits in each one of these points that we're using, or the least number. Least number is 2 significant digits. So if you're ever doing any calculations, you also take into account the way your table is. So here's our graph. Now, if we just connect the points, we get pretty much not really a straight line, which means technically on a line of best fit, by drawing a line of best fit, any 2 points along that line of best fit, doesn't really matter what 2 points we pick. It will still give us the same slope. In math, we think about the rate of change or the slope, the rise over run. But if the line is not straight, if the line is jagged as we had it, notice here the speed changes and we're not able to get an overall average. So what we do is we calculate, we draw what we call a line of best fit. So we draw our line of best fit, and then from that line of best fit, we can take any 2 points that we might feel. Doesn't have to be the points that are included in our table. It just has to be 2 points that lie along this line of best fit to be able to allow us to calculate ultimately the average speed of this object. Let's revisit a math equation here. Y is equal to mx plus b. This is our slope-intercept form for an equation. Y is equal to mx plus b. And it's relatively similar to the calculation delta d is equal to VAV times delta t. Now, before we panic and go, oh, is this a new equation that we've learned? No. Really, if we look at the equation VAV is equal to delta d over delta t, and if we look at our pyramid, how do we rearrange from our pyramid to isolate, let's say if we're trying to find delta d. So if we're trying to find delta d, we cover up delta d, and notice that v is side by side with t, which means we're going to multiply our speed times time. So all we've done here is rearrange the equation. We've not really done anything different. We've just isolated delta d because what axes are we labeling delta d with? What axis is delta d on? The y, which is the y. The VAV, as we're going to find out what the VAV stands for in terms of our graph. And then we have the delta t. So let's look at the comparison between the equation y is equal to mx plus b in math with the equation delta d is equal to VAV times delta t. The y is a dependent variable in the equation y is equal to mx plus b. It's similar to the delta d of our equation, which is the distance traveled. Now, in terms of x is the independent variable, which represents our delta t, or time. M, in our equation here, is represented by slope. The slope is equivalent to the VAV. So in other words, if we calculate the slope of a line on a distance time graph, it will allow us to calculate the average speed. So the average speed on a distance time graph is calculated by calculating the slope of that line. So the b value is the y-intercept of the line, but if we translate it to our distance versus time graph, usually the initial distance is always, or most of the times, starts at the 0 marker. And hence, the y-intercept would be crossing through the 0 point on the axis. So, slope of a line of a distance time graph represents the speed, or more importantly, the average speed, if we're looking at the line in terms of a line of best fit. So very important. So if you're graphing something, by calculating its slope, it will allow you to calculate its average speed. Slope and speed. The greater the speed, the greater the slope of the line of a distance time graph. Therefore, the steepest slope shows the fastest speed. Okay, so the steeper the line, the faster the object is traveling. So let's look at the following graph that shows the speeds of walking, biking, and inline skating. So here we have a graph showing the relative distance traveled and time it took for the person to travel either walking, skating, inline skating, or biking. So notice here with the colors, blue represents biking, there's fuchsia, skating, and the yellow is walking. Obviously, from the visual, without the need of numbers, we can tell which object is actually traveling the fastest. So, which is the fastest means of transportation, and how can you tell which is the fastest? Biking. Why? The steepest slope. So biking, steepest slope. So, following chart and graph shows the information of Canada's Joanne Millar's 200-meter individual medley race. The individual medley in swimming is all 4 strokes. So we're going to compare all 4 strokes and try to identify which of the 4 swim strokes is the fastest. So here we have a list of the numbers, our distance, and the time it took for it to reach each one of those time intervals. Now, from a whole bunch of numbers. It'd be a lot harder to try to identify visually which one. So you'd have to look through this table in order to pinpoint which object or which swim stroke is the fastest. So the best way to do it is to take all these points and to plot a graph. And there we have our graph. If we look at the following, which swim stroke is the fastest? The freestyle. The freestyle swim stroke is the fastest because, why? The steepest slope. So by looking at our visual, by looking at our graph, the steepest slope is the freestyle, which means the average speed would be faster for that one than it would be for the others. Which one looks to be the slowest? The breaststroke, because it's the one with the least steepest of the four. So let's move this little thing here. See that? So the slope of the distance time graph is determined from the rise over run, which also happens to be the distance over the time, which in turn is the speed. So what we do is we could take any 2 points. So let's say we took this point and this point. Again, try to find points that lie exactly along actual grid marks, if possible. Right? Anything that's kind of something like that, something that's along in the middle, it might not be as accurate, your numbering. So, from there, we calculate our rise and run. So our rise is our change in the distance. Our run is the change in time. And we've seen this in the last chapter where VAV is equal to delta D over delta T. So because our 2 points now are just random 2 points on our grid, we actually have D1, D2. We have down here T1 going to T2. So when we do make this calculation, VAV is equal to delta D over delta T, it's equal to our D2 subtracted by D1 over T2 subtracted by T1. And that will help us identify the average speed of the following graph. So, speed is determined from the slope of the best fit straight line of a distance time graph. So, let's look at our graph here. Distance, notice we've labeled our X and Y axes, or D and T axes. Distance in meters, time in seconds. So let's say we have our line of best fit. So there it is. So from the line of best fit, we pick 2 random points. Again, we try to pick any 2 points. It doesn't really matter. If you had a graph that was a nice clean graph and it had many great points to pick from, it doesn't really matter, because regardless, if we took the rise and run from any 2 points, any one of these points, it really wouldn't matter. It really wouldn't matter. It will still give you exactly the same slope. So let's say our run here was 2 units, or it would be 2 seconds. Our rise here would be, let's say, 4 meters. Using our slope equation, slope is equal to rise over run, we divide 4 over 2. But now in terms of VAV is equal to delta D over delta T, we don't have it as just 4 over 2. In math, they don't really represent any specific units. But in the physics component, when we are labeling distance versus time, the rise is represented by the units for our distance, which is meters, divided by our time, which is in seconds, which will give us now a slope, which is translated to our VAV of 2 meters per second. Because 4 meters divided by 2 seconds divide out to 2 meters per second. So, we have our line of best fit. We pick any 2 random points. Again, try to keep the 2 points within the the proper hash marks that lie along the grid. So here we have our run, which is equivalent to delta t is equal to 8 seconds. So from 2 seconds to the 10-second mark. We have our delta d, which is 7 meters. Again, remember, I've drawn my lines going this way. You could start off by drawing in your rise first, and then your run. It doesn't really matter. It doesn't really matter. So, we're still going from some D1 to some D2. We're going from some T1 to some T2. So it doesn't really matter whether you draw it below or your line of best fit or above it. So your slope is equal to rise over run, which is equivalent to VAV is equal to delta D over delta T. So if we take our delta T subtracted by D1, we get 9.0 meters subtracted by 2.0 meters. Our time, 10.0 seconds subtracted by 2.0 seconds, which will give us these units. It will give us 7 meters divided by 8 seconds. So let's write it down as 7.0 meters, because we keep the rule for the decimal places the same. 10 minus 2.0 will give us 8.0 seconds. So when we divide the two, we get an answer of VAV is equal to 0.875 meters per second. But again, the rule for significant digits, when we are dividing two numbers, we make sure that our answer has the same number of significant digits as the least number in our question. So the answer, we want these two significant digits, 0.87. We look at the number immediately following what we're taking, and the number rounds out to 0.88 meters per second, according to this table, or sorry, according to this graph. What interpretation can be made about the moving car if the line on the distance time graph for the car has the following characteristics? So here we have our distance time graph. So, question says a high or steep slope. So we just draw randomly something that would show some kind of steepness. Now, with respect to that, how would we draw our next line to show a less steep slope? And anything that would be obviously not as steep as our original one. But now, if we are wanting to show a zero slope, straight horizontal line. But what does that mean though? No change in what? In the distance. The distance doesn't change. What does change? The time, right? Time changes. Regardless of, whether you want it to or not, time ticks away. But you could be at a stop sign, your distance isn't changing. So your distance that you're traveling from that point, you're not really moving anywhere. So a horizontal line means time ticks away, but the distance does not change from wherever the position is.